Hi, in the last video we were talking about how in order to be more certain of capturing the true proportion, like if you want a 99% confidence level, you have to make a wider interval. So that can seem problematic, right? Because if you want to have really high confidence, like 95 or 99%, then you're going to have to make a wider interval and you're going to have less certainty about that. Sorry, you're going to have less precision about that. More certainty, less precision. But there is another way. There's another way that you can keep the same confidence and make a narrower interval. You have any idea what that could be? Well, if you turn the page, you might know already. It's sample size. So remember, our margin of error is dependent on this sample size. We're dividing by it because our standard error is dependent on the sample size. So if we sample more people, we should get a smaller margin of error, a smaller standard error, and a smaller margin of error. So we can actually take this formula and make a new formula by solving this for n. So if you love algebra, you're going to love this. If you don't like algebra, just skip ahead. It doesn't matter. We're going to be using this formula, which is now solved for n. And we plug all the other things in, and it tells us what sample size we need to get a certain margin of error. Okay, so if you like algebra, stick with me here. So what we're trying to do is solve for this n. I'm just going to take out, I'm going to simplify this a little bit. I'm going to take out the plus or minus. And take out the subscript, so it makes it a little bit cleaner. Okay, so we want to get this n out of the square root. Let's move the z star over first. So we're going to need to divide both sides. By z star, and that cancels those out. So we have ME, margin of error, over z star equals square root p hat q hat over n. Okay, we want to get the n out and solve for it, so let's get rid of the square root. So we need to square both sides. Okay, so now we have the margin of error over z star squared equals p hat q hat over n. Okay. Now our n is in the bottom, so we want to get it into the top, the numerator. So I'm going to multiply by n. I could also just flip the whole thing over. That's another way you could do it. So now we have n, oops, wrong color, n times margin of error over z star squared is equal to p hat q hat. And we're close. We've got n over here. We just want to move this to the other side. So we need to multiply by the reciprocal. Z star over ME squared. That's how it gets flipped down here. And then these cancel with those because it's the reciprocal. N equals p hat q hat times z star over the margin of error squared. Cool, huh? Okay, so that's how we get the formula if you're curious, but there's no need to solve this every single time. We just do it once and make a new formula. So let's see how this works. It's believed that 25% of adults over 50 never graduated high school. We wish to see if the same is true among 25 to 30-year-olds. Okay, so what this is saying is we're kind of using this estimate of p hat to start with. How many of this younger age group must we survey in order to estimate the proportion of non-grads to within 6%? So that means plus or minus 0.06. So that's our margin of error. with 90% confidence. So that's our Z, determines our Z star. Okay, so let's put this in. So n equals p hat. So usually they have to give us some kind of estimate that they either already kind of have an idea what it is. We're going to use 0.25 in this case. And then q hat is the complement, 0.75. Z star, so that's 90% confidence. I'll find my page for that. %, was 1.6449. Divided by, this is the margin of error we want, right? So this is now an input. How many people do we need to sample to get this margin of error? And then we square it. Okay, so we punch all this in. Again, I'm going to do it in all one step. 0.25 times 0.75 times, or just parentheses would be fine. I do have to have parentheses here because I want to square this whole quantity. So 1.6449 divided by 0.06 squared. Okay, that's 140.9. I'll say 140.92. However, we can't survey 140.92 people, right? We're talking about people now. So we do round, so this would be 141 people. Even if this was 0.5 or below, we would still round up, because to get that margin of error we need at least that many, so we would round up. So I'm going to write a note here, always round up. Okay, let's do one more example. Suppose we want to cut the margin of error to 4% again. Again with 90% confidence. What's the necessary sample size? So do you think we would need to sample more people or fewer people? Let's find out. So n equals 0.25 times 0.75 p hat q hat. Everything else is staying the same except our margin of error. So our 90% confidence is 1.6449. That's our Z value. And 4%, now this is 0.04 squared. .25 times 0.75, sorry, I can't see that, times, or just parenthesis, because calculator recognized parentheses as multiplication, 1.6449 divided by 0.04 squared. 317.07. Okay, so this is an example of where, even though it's 0.07 of a person, if we want 4%, we have to go up, not down. We have to sample at least this many people. So this would be 318 people. So it went up. So to get a smaller margin of error, we need to sample more people. That makes sense, right? The more variability you're going to have with the fewer people you sample. So let's summarize that. What's the relationship between the number of people sampled and the margin of error? To get a smaller margin of error, we need to sample more people, or more auto parts, or whatever they are. We need a bigger sample size to get a smaller margin of error. Okay, that's it for this video. Thanks for watching.